In this work, we studied the problem of garment opening insertion for robot-assisted dressing. During the insertion stage of dressing, the contacts between the garment and the body are particularly important, and in many cases robots have to take advantage of them to complete the task. To this end, we propose a model predictive controller with a learned graph-based dynamics model. In every time step, the point clouds of the opening and the body are extracted from the robot's camera. The point clouds, along with the robot's action, are then converted into a relational graph. We use two relations. With the first one, we aim to model the deformation dynamics of the garment's opening, and with the second one, we aim to model the contact dynamics of it with the body. The actions are encoded in the feature vectors of the nodes. The controller resembles a number of candidate actions, and a graph is produced for each one of them. We use an attention-based relational graph convolutional network as our dynamics model. For each of the candidate actions, the model outputs a predicted point cloud of the opening of the next step. Then, the action that minimizes a cost function is selected. The cost function aims to maximize the coverage between the body and the opening and minimize the distance to a certain depth. To collect data for our model, we build an environment in PyBullet with a ring-shaped cloud object as the opening and general geometric solid objects. To simulate effects from the rest of the garment and randomize the dynamics, we apply random forces on the opening. We found that our model achieves more accurate and robust predictions against state-of-the-art methods for deformable object modeling with external contacts. Moreover, we perform experiments in 4 real-world dressing scenarios. As a first baseline, we compared against a vision feedback controller that aims to align the opening with the targeted body part. We noticed that this controller succeeded consistently only when the opening was wide open and the garment was relatively stiff. We compared with the second baseline, in which we substituted the coverage term of the cost function with the distance between the centroids of the opening and the body part, a common logic in robot-assisted dressing. We noticed that the controller led the opening towards the center of the body part, and therefore the sides of it were often caught on the body. Finally, our proposed method achieved high success rates on all dressing scenarios, even with garments with narrow openings like the hospital gown's sleeve and high deformations like the scarf. Thank you for watching.